management 2 is about methods of TQM. This means total quality management. And regarding the tools, so it is more about management. These are management methods, not so much statistical tools. Sometimes it is also with statistical tools, but here we have more management methods which are focused. Okay, the beginning of total quality management was who's a physician, an expert in statistics called William Deming in the US. He was a professor for statistics in New York at the university and at the Columbia University, and he developed methods for QM improvement in the USA. These methods were not so much noticed at first, but then later on in the 50s, 60s, 70s, he was consultant for Toyota in Japan and founder of the Toyota production system, which was very successful. And then later on in the 80s and 90s, the methods of Deming become more and more popular, and they were overtaken worldwide into quality standards till today. For example, the ISO 9001. Well, one of the biggest things Deming developed was the quality circle, like I see it here, for continuous improvement process. There's nothing which cannot be done better. So this means plan, do, check, and act. And if the result is okay, try to make it better if it's possible. So it's a way of continuous improvement, a continuous improvement process, and every company has a continuous improvement process. And the auditors in the audits, they ask, do you have such a process implemented in your company? What are the goals of Deming? The goals is a process-orientated quality management. This means, on the one hand, a high production quality level, a high production precision. This means not much variation, low variation. Without variation, it's not possible, but very low variation. This is the goal. Continuous improvement process, like I said before. Expansion of the market share, so more projects at the company, and at least higher profit of the company. In practice, if we have a new project, the beginning of a new project is planning, simulation, prototyping. Then we have first series products, but it is the beginning, it's a trial, it's a beginning of the series production, not the real series production, it's a test production, the first run. And then we have some optimizations. And after this, all these things, in all these phases of development, we have only small volumes, small samples of the parts. And if a new process is running good, running well in a laboratory or in a development department, it does not mean that the series production is okay. Series production often shows problems which are not raised in the first phase, in the test run phase, in the development phase. Series production means a production of 100,000 parts a year or millions of parts a year. And for that, the process must very robust and must very constant, continuous, and only very small, very low variations are allowed. To reach that goal, we need, on the one hand, statistical methods, statistical tools. We will talk about this in QM1, like we did before, and management methods. And some of the management methods in TQM we will see here in QM2. I will give you an overview over these TQM methods. Now we have passive methods for quality analysis, for monitoring of quality samples, and extrapolation of to make a forecast, a prognosis of the quality of the series production. This is always a big topic and a big goal, to have measurements of samples and to do a forecast on the series production on a higher volume. And this is something which we will see in QM1, how this can be done. And this will, of course, be one of the homework questions later on. You will see this. It will be some questions will be related to the extrapolation, to the forecast of sales quality on the basis of samples. This is a thing which is very important in the industry, because mostly you have only samples. You cannot test every part. It's much too expensive. Quality optimization. These are not passive methods, only measurement of the quality performance and monitoring. These are active methods. Here we have a variation of parameters, of factors, of process parameters to find a process optimum, the highest quality level which is possible. Then in the management methods, we have the TQM methods. We have quality indicator values to make a monitoring and a ranking of the different departments in a company. And we have the continuous improvement process. So we have quality-orientated processes in the whole company, overall departments. It includes the management, also development of technology, the employees, and we have the Six Sigma. The Six Sigma method, which is a toolbox of different methods. Six Sigma is the highest standard in quality management. Well, this sheet shows the principle of Six Sigma, and it begins with the definition of the process of the project, including customer requirements and quality characteristics, measurements, and so on. Then quality is measured. So the current process is quantified. Then they find out problems, for causes for defects, for example, and they try to find out what are the causes for the reasons for the defects. Then the improvement process, and then in the production later on the validation of the process, the control, the monitoring of the process, and long-term tests. Six Sigma means a lot of tools, statistical tools, like you see here, some things are here shown here: Ishikawa, FMEA, SPC, DOE. I will show you some of these tools in the lecture later on. Six Sigma means you need experts who are doing this in the companies, and there are some companies or associations who are doing this qualifications, or they are offering courses, and the engineers and the company go into these courses and get training in Six Sigma methods. It begins with green belt. A green belt, it's a little bit similar to the martial arts system of Japanese martial arts. Yellow belt means technical expertise, competence, few method competence, but not very much. And about 25% of his work time is for Six Sigma projects. He supports the black belts, and he's getting a training course over 2 weeks. And he has his his own Six Sigma projects, but these projects are very small. Next step is the black belt, the qualification to the black belt. The black belt has a high technical expertise and competence, and also a high method competence. He knows about the TQM tools. In many cases, it is a junior manager, and he works only in Six Sigma projects, at least 1.5 years long, and supports the master black belts. He's trainer for the green belts. He or she, of course. Presentations, he's doing presentations and has his own projects, Six Sigma projects. The highest qualification level is Master Black Belt. He's in the first management level, a lot of experience in Six Sigma projects, very high method competence, and he works only in Six Sigma projects. In the companies is the internal trainer, and is doing the strategic planning of important projects. And some of the biggest companies, they have one level above. This means the champion level, and he is for the Six Sigma level for the development of the whole company, and together with the general management. And he controls all the teams, does presentations at the customer, at congresses, and so on. So he's the Six Sigma leader of the whole company. But this is only a thing. A very big company have this champion level. Most of the normal companies are ending with black belt or master black belt level. Here we see on this sheet, we see some of these tools in the Six Sigma toolbox. And these methods you see here are typical TQM methods of total quality engineering. It starts here with QFD. QFD is in the beginning of the planning of a new project. This means quality function deployment. It's about the requirements of the customers, of the end user, to a new project, to a new product or a new project. Then we have the Ishikawa method, fishbone, 5M method. Then we have the FMEA, failure mode and effects analysis. I will show you later. Also DOE design of experiments, also SPC, statistical process control, and POCA-UCA. These are the most popular PQM methods, and they have an impact on the quality. Of course, these methods, which are used in a very early phase of the design and planning process, these have the most impact. The later the method is applied, if it is in the production, the impact maybe is not as high as the impact if we use the methods directly here in the planning phase. What means Six Sigma? Six Sigma means, what it means, you can see it here on the sheet. Let's say we have a dimension, a length dimension of 60 millimeter, and this is the mean value. And then we have standard deviation. Maybe you test 10 products, 10 parts, take 10 parts out of the production. You have this mean value. And then you have a standard deviation. This is one standard deviation. This is 2 standard deviations. This is 3 standard deviations, 4, 5, 6. Mu is the mean of a very high number of parts, maybe 10,000 or whatever, 100,000. So the whole production. And sigma is also the standard deviation, not of a sample. It's the standard deviation of the whole production. And this is 1 sigma, 2 sigma, 3 sigma, 5, 6, 4, 5, 6. This is 6 sigma here. And now 6 sigma level means that plus 6 sigma on the right side of the mean and minus 6 sigma here on the left side of the mean. This must be inside the tolerance. Here is the lower specification limit. Here is the upper specification limit. Between this is a tolerance. And 6 sigma means that the whole production is inside the tolerance with 12 sigma, plus 6 sigma and minus 6 sigma. This is meant with 6 sigma. And what does this mean? It means that not the drawing is the goal to reach for the production. The production has only the half of the tolerance, because plus minus 3 sigma means in this limit, between these limits here, plus minus 3 sigma means 99.73% of all the parts are inside these limits, plus minus 3 sigma. And if you want to have 6 sigma level, you must make sure that your production quality of the parts is between these 2 limits, plus minus 3 sigma, because then you have nearly 100%, not totally 100%, but nearly 100% good parts. And if you want 6 sigma quality, only 4 parts per million, which are poor, which have defects, are allowed. And to reach this goal, it is necessary that your production quality is only the half of the tolerance of the drawing. So if the drawing shows 60.04 on the right side of the mean, or of the target value here, and here on the left side 59.96, then this means the production has only these limits here of 59.98 and here 60.02. So it's half of the tolerance which the production has. And the production precision must be that way that nearly all the parts, 99.73% of the parts, are between these plus minus 3 limits. This is necessary for Six Sigma performance to reach this goal here, Six Sigma. So what the designer has to know, if the customer wants Six Sigma level, then this means that every tolerance in the drawing, they can divide it by 2. It is only the half of the tolerance which they have in reality in the product, if Six Sigma level is required by the customer. Now, for this, you need a lot of planning. And some of these methods, quality planning, are these TQM methods. And I will give you an overview about these TQM methods here in this chapter. At first, I would tell you something, give you some information about a method which is called QFD, House of Quality. House of Quality means, QFD means quality function deployment. And the main thing, the main tool in this method is the House of Quality. Here in the House of Quality, the company is checking the customer requirements. In most cases, this method is performed by the end company, which brings a new product directly in the market. So they are making question actions. They are asking people on the street, what are your requirements on a new product, and then they put all these requirements in a list, and then in the planning process of the new project or a new product, they have design requirements and quality characteristics, and then they fill out a relation matrix, the relation between the quality characteristics of the most important quality characteristics of the new product, and here the customer requirements. And then they can do an evaluation and a comparison with other products, similar products on the market. So the goal here is to find out what are the most important quality characteristics which meet the requirements of the customer. This is a tool in the beginning of a new project or product to find out which quality characteristics are the important characteristics to meet customers' requirement. So the main goal is in QFD is a detailed analysis of the requirements of the customer on the new product, and to get information for the following process steps, which is design, production, quality control, and so on. So QFD is the basis for customer satisfaction, means meeting the customer's requirement. In B2B, business to business, if there is a supplier company and a customer company, then they use the method, QFD method, to find out what the customer company wants and what are the most important requirements. So to get the knowledge, what is most important for the customer company regarding a new product. This is important for development of partnerships between supplier and customer, especially if it is if they want to develop new products together. Well, just let me give you an example here. This is an example. I have this sheet only in German, but it is no problem. It is an example of a water pump housing. Here you see the requirements of the customer, and I will translate this here. This is the dimension precision. This is a high lifetime of the pump housing, a smooth surface, low costs, and a smooth an equal surface. No differences in the surface on special areas of the part. Here you see the quality characteristics. It is important outer diameter, it's a flatness, the roughness. Here it is the cycle time, the number of cycles if the part is stressed by a dynamic but dynamic process, so pressure goes up and down, and then the question is what is the number of cycles, up and down cycles, which the part is doing before getting a crack or something like this. Then here weld lines and the material and of course the price of the part. So they have some important quality characteristics here, and they bring this in relation to these requirements of the customer. And this is here done with this matrix. One is a low relationship and 3 is a strong relationship. So then they have the result at the end is to find out which are the most important parameters, the most important quality characteristics here to get most of the customers' requirements and to meet the customers' requirements. Of course, there are in the literature, you will find a lot of different houses of quality. They can also integrate similar products which are on the market from other companies. They can also integrate this here in this house of quality. But this is the main thing, matrix for the relation of the customer requirements and the quality characteristics. QFD is a method which is mostly done by the companies who are the end companies. This means who bring a product into the market and they are asking the people on the streets or whatever, a group of people, target people, about their requirements. It's not so much used in the B2B business from between supplier and customer. One of the PQM methods is the Pareto analysis. Pareto was born in Paris. He was an Italian engineer and economist, and he works as a professor in Lausanne in Switzerland. And he has invented the 80-20 rule. This is the Pareto principle. He found out that in Italy at that time, 20% of the people, of the total population in Italy, got 80% of all of the money, of the entire capital. So this means of all of the money. He was working for a bank or for several banks. So he said, okay, this means the efficiency would be an optimum if the banks only care about these very rich persons, only these 20%, because they own 80% of all the money in Italy. This is the Pareto rule. Well, how we transfer this into practical quality assurance? Well, if you have the data, defects data, quality data of an industrial production, you can do a classifying and an evaluation of the data. You can find out what defects are the most important defects, which are the critical defects or the main defects, and what defects are unimportant. And this is important for the visualization. If you make a presentation, it is not so good to do everything with a table, with tables, because tables are not so good. Better it is you have a diagram or a figure, and you can show it in a good visualization form in a presentation. This is the basis for convincing customers and also the department managers or the general management, of course, in the company itself. What does this mean in practice? At first, you have the measurements of data. Let's say you check the problems or the defects in a production over 1 month. And then you see several defects caused by this reason, and then another reason for another number of defects. So you measure all the defects, all the problems in a production over a period of 1 or 2 months. Then you do a ranking of the data, a classification of the data. This is the sample size, and K is the number of classes. You can put these single values in classes. And then this is an equation here for the width of a class. And then you do a visualization. And this is the result of a Pareto example. Here you see several causes for defects, or the defects itself. Defect A, defect B, defect C, D, E, and so on. And what you see here is, in this production, only 2 defects, defect A and defect B. These 2 defects cause 80% of all the defects. So it makes sense to concentrate on the optimizing of these 2 defects. The other defects are not so important. So they say, okay, let these defects be, let it be, because they are not important. But if you find solutions to optimize these problems here, these 2 defects, then you have solved 80% of the problems in the production. This means Pareto. And here this visualization shows, in this diagram, shows very good. On one view, you can see we have these 2 defects, which are the most important ones, and these are the not important defects. This is the sum curve. It's the same thing. If you add the frequency here of these different defects, after you have summarized all the defects, you have 100%, of course. It starts with 49% here of defect A, then we have the 31%, we have 80%, and then here the next C, then the sum is 86, 91, 96, 99, and 100%. So this is the sum curve here, but the Pareto chart is here, these red bars. Here an example. we have here in our university, we have a study course called dental technology. And this is here a video analysis which some students made in the study course dental technology, and they found out here they make an analysis in a dental laboratory. They make an analysis about I think 2 months, for 2 months, over 2 months, how many problems they have, how many defects they have in 1 month, let's say 1 month. There were 6 cracks in plastic bases, 5 broken plastic bases, an artificial tooth is fallen out 4 times. Then 1 time plastic surface delaminations, broken clip and broken sublingual clip. So they have these different defects, kinds of defects, and here they have the frequency, how often these defects occur in the dental laboratory. So this is a simple visualization of the problems, and you can say here, okay, if you concentrate on these first 3, then you have more than 80% of all the problems solved in this dental laboratory. Let these remain, let these be, but these 3 here, these are the defects to concentrate on and to find solutions for optimization for that. This is a Pareto principle. The next PQM method is Ishikawa, also known as a fishbone diagram, and showed you some of the Ishikawa things before. The inventor of Ishikawa was a professor in Tokyo. He was a chemist, and he was the inventor of the fishbone diagram. And this is until the Second World War, it is used in many applications. In many industry companies, they used the Ishikawa method. The goals of Ishikawa is a brainstorming by the use of the 5 or 6M, and to think about the cause and effect relations regarding defects or problems, regarding a new product. This is a systematic preparation of the following FMEA, to think of all the possibilities and to forget nothing, to avoid to forget something. This is only an example here. You see here, man, material, machine, methods, milieu, or mode. These are the 5 or 6M. And what they are doing here, they have a cross-functional teams with members of all the departments in the company, design department, project management, production, quality assurance, and so on. And then they think about, they sit together in a meeting 1 or 2 hours, and they look at the drawing. They don't have any parts at that time. It is in the quality planning process. And then they think about what can go wrong regarding the requirements of the configuration, the documentation, and so on. And so they ask what can go wrong related to the operators, the man, the material, machine, and so on. All these things, they try to find out what are the causes and what are the effects, what are the results. And then they try to find solutions for avoiding these causes of problems. But this is in the next phase. This is in the FMEA. Here in this phase, they only try to find out what are the causes and what are the defects caused by man, material, machine, methods, and milieu. So Ichikawa is a preparation of FMEA. FMEA means failure mode and defect analysis, and a lot of companies use FMEA. Actually, in an audit, the auditor wants to see if there were FMEAs performed in the company. And also the big customer companies, automotive, medical, they want their suppliers to do FMEAs in the beginning of a new project. It is a risk analysis, and FMEA is nothing else than a risk analysis. What can go wrong with a new project, with a new product? The goal is a process capability of 2. We will see what this means afterwards when I show you the sheets of SPC. CPK means the capability, the process capability factor. And CPK2 means Six Sigma, and Six Sigma means 4 ppm maximum, not more than 4 parts per million that are defective. How to reach that? At first, it is important to know that most of the impact on the quality is done in the planning phase, in the early phase before the production is running. And a lot of these TQM methods are used in this planning phase before production. Of course, they have some methods in production, that's right, but it's not so much for optimization, it's more for monitoring. SPC is for monitoring, POCA-YOO is for optimization. But most of the TQM methods have the biggest impact if they are used in the planning process before the production starts. There are 3 types of FMEAs. The main types is the function FMEA, the design FMEA, and the process FMEA. A function FMEA can only be made by the end customer company who brings whole product into the market. So this means a function FMEA of a car can only be done by VW, Mercedes-Benz, Ford, General Motors, these companies who are launching their products into the market. Only they can do a function FMEA. All the many suppliers of these companies cannot make a function FMEA on the whole product, on the end product. They can do only a function FMEA on if they make a system like a pump. Then of course they can do an FMEA on the function of the pump. But if you have suppliers for parts or for components, many times the function cannot be tested. And then the supplier company has 2 kinds of FMEA. This is the design FMEA for the geometry and for the design of the product, and a process FMEA. This is the FMEA for the manufacturing, for the production. An FMEA has 4 criteria. The first criteria is the probability of occurration. There is a cross-functional FMEA team in the company, and in the FMEA team, there must be a person, an experienced person of the design shop, project manager, a production, maybe a shift leader or someone from the production, someone from the purchasing, the quality assurance. So it is a cross-functional team of about 5 or 6 members. And these people are sitting together in a meeting, mostly 2 or 3 hours, and then they ask on a new product, they ask what is the probability that a defect, a special problem occurs. If there's no probability, the defect gets a ranking number of 1. If the probability of occurration, so this means the probability that the problem happens, that it comes to reality, if this probability is very low, they give a 2 or 3 to the defect or the problem. If the probability is low, 4 to 6. If you have the middle probability, 7 to 8, and high probability means 9 to 10. So this is a ranking list that this defect will happen. And you have to do this with every defect that the project FMEA team has defined, has found out. For every single quality criteria or for every single kind of defect you have to make this ranking here. This is the ranking number here, the points. Well, the severity, this means how important is it for the customer. Also, again, the ask for every defect, they ask what is the probability for severity. So for that's a problem that the defect is important for the customer. If there's no probability, the defect gets a ranking number of 1. If it's low, 2 or 3. If it's middle, 4 to 6. And middle to high, 7 to 8. And if the probability for severity is high, then the defect gets a 9 or a 10. And the third criteria is the probability of detection. What is the probability to see the defect in the production and to detect it? If there's a high probability of detection, the ranking number is 1. If it is a middle probability of detection of the defect, it is 6 to 8. And if it's very low, no probability of detection or very low probability, the ranking number is 10. So you have these 4 criteria: occurration, severity, and detection. And you have these 3 numbers, ranking numbers, for every kind of defect, which the team has defined, has identified. And now, the next step is to calculate the number of risk, which is NOR. This NOR is the number of risk and is only the multiplication of these 3 criteria: occurration, severity, and detection. And then they get a number, multiplication of these probabilities here, of these ranking numbers, has a result for every defect, a result in this number of risk. And now the thing is, some companies say, if this number of risk is higher than 100, then they have to look at this kind of defect and to find a solution. If it is lower than 100, it is not important. The other thing is, other companies say, okay, everything which is higher than 120 is important, and if the number of risk is lower than 120, they do not care about it at the moment. They concentrate on the higher numbers of risk, on these defects with a higher number of risk. This is not common. In several companies, they use 100 as a limit, or other companies, they use 120 or 130. Important is that an FMEA is not a one-day fly. This means not only performed one time, but after the planning phase, the old FMEA has to be reviewed, and they want to check out if it is valid or if it is not valid. So they have to make a review of the FMEA before starting the product. FMEAs is a very popular tool in quality management and is done by many companies. Here you see the process chain. This is the cycle of the quality. TQM methods are integrated in every step of the quality cycle. In the beginning, we have the customer requirement, then we have the product design. And if you think about product design, we have prototyping, we have simulations, we have some CAD studies, maybe we have material database analysis to find out the right material for the application, for the project, for the product. The next step is the process planning, maybe tooling, quality planning, planning the tests of the new product, and the process, the planning of the process, production process. And here they use Ishikawa method and FMEA method. Then if the process is built up, the machine is there, and the tooling, the mold, and so on, the material, then they can do a first run. And here they're doing DOE, design of experiments. This also is a very powerful method in TQM. And the goal here is to get a robust design, that the process is not sensitive against disturbances, external disturbances. This means if that process is not sensitive against changes in temperature. You have changes in temperature in the production hall from summer to winter. In summer you have 40 degrees Celsius, and in winter maybe you have, don't know, 20 degrees Celsius, and the production must be robust against these things, and it must be robust against changes of the material batch or whatever. And this is a goal of DOE, of design of experiments. We will talk about this later on next Wednesday. Here we have the pre-production. The pre-production is also on the basis of DOE, optimization, process analysis, with the goals of robust design, machine capability, and process capability. Then, when the project comes to production, we have incoming inspection of the material or of purchased parts. We have also online process control, SPC, maybe camera monitoring, long-term optimizations, and always the training of the employees. In some cases, a new product needs service, so we have customer service and continuous quality improvement. So this is TQM methods in the application over the process chain. Most of the problems in the production are caused, have their reasons, in the planning phase. So 75% of all the defects which we have later on in the production have the reasons here in the planning phase, in the design and the tooling, in this early phase of a new product. The later the timeline is here, and if we are in the production, it is very expensive to optimize the quality. It's most cheaper to optimize the quality here in the planning phase. And that's why FMEA is such a powerful tool, because you can use FMEA in the planning phase and you can think about all the possible defects, what can go wrong with a new product or with a new production. And the better you do this, the more money you can save later on, and the higher is the quality level. The elimination of quality problems in the production, it's expensive on one hand. On the other hand, in many cases, not so efficient and not so possible, because all the machinery is there, all the tooling is there, the materials are there, you cannot change a lot. Here in this planning phase, you can change something, you can make simulations, you can make prototyping analysis to get a robust production later on. If you start the optimization here in the production phase, it is much more expensive and a lot of work. Here it makes sense to do the application of TQM methods here in the beginning of the planning phase, in the beginning of a new product. Yeah, and here this shows it again. If you put a lot of ideas and knowledge here in this planning phase, you can reach an elimination of 80% of all defects. 80% again is the Pareto principle. And this is the basis to reach this goal of Six Sigma or CPK2. A high process capability can only be reached, or Six Sigma can only be reached if they do a lot of preparation in the planning phase. And this means FMEA and all these things, as I showed you before. When all this is done, then in the production, they have a TQM method, which is called SPC. SPC means statistical process control. And statistical process control means to take out samples out of the running production. So if you have a production, produce products, doesn't matter what kind of products you take out, every hour or one time a shift, you take out a sample of 3 parts, of 5 parts, of 10 parts, depends on the product. And then you measure these sample parts. And you do this one time a shift, and then the next shift, and so on, and over some days and some weeks. And then you get constant information about the quality of your process. The process here, Ishikawa again, depends on these 5M: man, machine, material, methods, milieu. And out of the process are coming the products, and you take out samples out of the production. And then one time a shift, you get measurements, sample measurements, and information about the quality. And there are 2 possibilities. One possibility is that the quality is okay, then everything is fine. If the quality is not okay, then there are 2 possibilities. And the one thing is corrective actions on the product. This is expensive, and you have to do this with all the products. So you have to test all the products and find out what are the defective products, and then you have to make corrective actions on every product. Sometimes this is not possible, and if it's possible, it's very expensive. So this is not a very good solution and has to be avoided. The sense or the goal of SPC is to do corrections in the process to bring the quality in the tolerance field again. If the information about the quality is not good, so if you have defects, if you are outside of the tolerance, you must do corrections in the process to get inside the tolerance. So it's a preventive method to optimize the process before you have too much scrap parts or scrap products which you cannot use, you cannot sell. And this is the goal of statistical process control, on the basis of the sample measurements, to make a control of the process. The tool for this is a quality chart. For every quality characteristic, you need a special quality chart. This means every dimension which you use for the SPC, you need a quality chart. This means you can only do SPC with some quality characteristics, not with all these dimensions in a drawing or with all the things which are important. You have to focus on the 3 or 5 or 7 most important quality characteristics. And with these, you must do the SPC. You cannot do it with all the 100 dimensions which are in a drawing of a part. You can do it only with the most important quality characteristics. And if you have a quality characteristic, you can generate a control chart. And this is an example here for a control chart. 6 o'clock you take out 3 parts out of the production. This is the mean value. Here at 9 o'clock, also 3 parts out of the production, measuring. This is the mean value, only related to this quality characteristic here. The quality chart is only for one quality characteristic. Then at 12 o'clock, at 18 and so on. So this is the timeline here, and every 2 hours or one time a shift or whenever, it depends on the product. There is no rule of the time, of the points of time here. This is, you can choose this as you want. But quality control chart has mostly 100 or 120 measurements on one chart. There are two kinds of quality control charts. One option is if you don't have tolerance limits, the customer has no tolerance limits for this quality characteristic. Maybe the weight of a plastic component, of a plastic part, there is no tolerance given by the customer. This would be an example. And in this case, you have an upper control limit here and a lower control limit here. And inside this area, you have an upper and a lower warning limit. This is the target value which has to be reached. And warning limit means if a measurement, if a sample is above or below the warning, the warning limit, then you can let the production run, but you have to increase the test frequency. You have to make more tests to make sure that next time the performance is inside the warning limits again. If a value is outside the control limits, then you have to stop. You still have to stop the production and find out the reason and make optimizations to bring back the quality in the area between the control limits. It's only allowed to do the production inside the control limits. Outside is not allowed. If you have control limits, if the customer has defined control limits, so in every drawing there are control limits, of course, then they have, if the customer has the tolerances defined in the drawing, then you have an upper specification limit and a lower specification limit. Between the specification limits, this is the tolerance. And now you have inside this, you have an upper control limit and a lower control limit. So you have the specification limits outside here and the control limits inside. And now the goal is to keep the process inside the control limits. If there is a measurement outside the control limits, you must do an optimization on the process to bring the quality in the area between the two control limits. And this is with this method, you cannot produce scrap because you react, you do an optimization before the quality gets outside, runs outside of the specification limit. Outside of the specification limit, you cannot sell a product. Then it is a scrap product. You cannot sell it. It is waste. So the goal always is to keep inside the control limits and to avoid that the qualities, the measurements are running out of the specification limit. This is the goal of the quality chart with control limits. In many cases, SPC is not a direct process control. It is more a monitoring of the quality. It's a documentation of the process or production quality. So SPC is for monitoring, for documentation of the quality. It allows economic process monitoring by sample tests, and it allows studies on the process capability, including long-term quality documentation. We will see what is meant with process capability. We will see this a few sheets later on. SPC is a preventive method in the production to avoid scrap. The basis for SPC is that there is only a random variation, a variation by chance. No systematic disturbances are allowed. In many productions, you cannot make sure that there are systematic disturbances, but you have to eliminate systematic process disturbances as far as it is possible. That the process variation is only random variation, only a variation by chance. This is the basis for all the equations for SPC. You can, if you do this, if you perform SPC in the production, you have an objective documentation of the quality level. You have real measurements. You have long-term analysis, trend analysis, and you can detect problems of the process before you get scrap parts, before the production is running out of the tolerance. Yes, you get a high knowledge and transparency of the process. What are systematic disturbances? Systematic disturbances must be avoided. What are examples for this? Examples can be a wrong assembly of the production equipment, or a wrong or exchanged production equipment, broken tool parts, wear of cutters, a change of machines, production lines, assembly lines, variations in the material, humidity. So this is the environmental conditions here, the milieu, humidity, temperature. Also, systematic disturbances can be if you change the measurement equipment, or the measurement equipment is not capable for the product. Wrong sample sizes or intervals of testing, and of course the man, the operator, qualification may be too low or no concentration, no motivation, whatever. Now, in the quality chart, you can include single values, or the arithmetic mean, or the median, or the range, or the standard deviation. So mostly in the industry, they use the arithmetic mean of the sample for these quality charts. So every point in the quality chart is the arithmetic mean of a sample of 3 parts or 5 or 10 parts. It is the arithmetic mean of the sample. This is only the mean. The other information is the variation, and the variation, for this you have a variation information about, and here mostly the standard deviation is used. So in a quality control chart, you have the mean and you have the standard deviation. You can also use the single values for the quality charts, or median or range charts is also possible. Here an example, here you see the this is a single value chart. Here, mostly here you have three or two sample size of 3 or 2 parts measurements, and here you see the dates, and you see it's from May to October, is a half year. It is the quality performance. You can do a long-term trend analyzing. You can see here in this example that the quality is very constant and very good, very low variation here over a half year, over 6 months. And here in the result table, you see the upper and lower specification limit. You see the sample size of the whole quality chart, 111 measurements. This is the sample size N. Here you have the mean, the standard deviation, and here the maximum CP and CPK and the minimum CP and CPK values for the process capability. Well, there are 5 types of failures in quality charts, and if you have a computer-aided system, a quality system, the computer gives you an alert, and if one of these 5 types of failures occurs, the first quality chart here on this sheet shows the process under control. Here you have a distribution. By chance, it is a random distribution. The process is under control. And this means that 2/3 of all the measurements are in a 1/3 range around the target. This is the target here in the middle. And 2/3 of all the measurements, 66% of all the measurements are in a 1/3 range around the target, 1/3 of the tolerance. Well, this is the goal. Now, to get an alert, alarm information of your quality system, if one of the measurements is going out of the upper control limit, or here is lower than the lower control limit, then you must interrupt the process and optimize the process to get back inside the control limit range here. This is one type of failures in a quality chart. Another failure can be a run. A run is if you have 7 values at least on one side of the mean. This means above or below the mean, at least 7 values. This can be a systematic failure, and that's the reason why you get yes, an alert of the computer-aided system. This is called a run. Even if the quality is inside the control limits. This is an example for a trend. If you have at least 7 values increasing or decreasing, then you have a trend. Also can be a systematic failure. Also, a problem can be if there are too many measurements nearby the control limits, upper or lower control limit. This can also cause a failure alert of the computer system. Too many values are nearby the control limits, and here this is also a problem because too many values are near the mean. This problem here is called middle third, because here you don't have 2/3 of all the values in a 1/3 area around the target. Here all the measurements are very close to the target and too many values are near the target. This can be that the upper and lower control limit is not calculated correctly. Well, what does CP and CPK mean? At first, the first step is you must calculate the machine capability. This is a short-term capability. Usually 50 single values are used. So you produce 50 parts and measure them, one characteristic, let's say one dimension. And for this dimension, you have an upper specification limit and a lower specification limit. And the CM factor is this tolerance area divided by 6 times the standard deviation. So these 50 measurement values have a standard deviation. And if you take it times 6 here, and you can do this equation here, and you see this is CM. CM is only the tolerance field related to 6 times the standard deviation. Then you have CMK. CMK is, there are 2 equations. One equation here integrating the upper specification limit, and here the other one integrating the lower specification limit. And the smaller value, you calculate the CMK with both equations, and the smaller value is the correct one. This is shown here. This is a normal distribution. Here you have an X bar. This is the mean. And if the mean is closer to the upper specification limit, then you take this, because then here over the line, this here is smaller. The distance between the mean and the upper specification limit is smaller than to the other side, the distance between mean and lower specification limit. So the smaller one is the most critical one. And in this example here, it is the distance between mean and upper specification limit. This means this one here should be the smaller CMK value. So this is the correct value, CMK value, which you take for your analysis. In most of the companies, a CM and a CMK requirement of 1.67 or more is valid, is a requirement. Here you see the explanation for the specification limits, and here the mean of the 50 parts and the standard deviation of the 50 parts. This is in a pre-production. If you are in a series production, you calculate CP and CPK values. CP is process capability. This means here again the tolerance area, and here 6 times the estimated standard deviation of the whole production. It can be estimated with this equation here, or it can be estimated with this equation here. You can also calculate the confidence limits for sigma. I show you later on in QM1 how to do this. CPK has 2 equations. This equation is with upper specification limit. This is with the lower specification limit. And the smaller value for CPK is the correct value. Usually, CP and CPK requirements is 1.33 or more. If the n factor is a table factor, the table factor is if you use a sample size of 3 and it's 3, then you have this factor here, 1.69 for the n. If the sample size is 5, you have 2.326 for the dn. So this is it depends on the sample size. Process capability is to be calculated for a quality chart with minimum 125 values and measurement values at least. This is the requirement for the process capability. So you need a lot of measurements before you can calculate CP and CPK. And CP and CPK are the values for the process capability. These CP and CPK values are high. You see here 1.0, 1.3, 1.67. The higher CP and CPK is, the lower the variation is, the better the process precision is. This is the mean chart. This is the standard deviation chart. And you see if the CP and CPK gets higher, then the standard deviation gets lower. So the precision of the process quality is better if the CP and CPK values are high. There is a book, you can have a look at this. It is about world-class quality, and it's a book. The author is Mr. Bode, and he showed an analysis on several suppliers. I think it was more than 20 suppliers in the automotive industry. Here in the US in the 70s, they have CP and CPK values of 0.67, which is pretty bad. Then US in the 80s was a little bit better. These companies had CPK values of 1.0. In Japan, they had values of 1.33 in the early 80s, and in the mid of the 80s, they had 1.67. And in the meantime, many companies, Motorola and big companies, they require a CPK and a CP of 2, which is 6 sigma. This is the goal for many big companies like General Electric or companies, very big companies. And they require this also from the suppliers. And if the supplier says, okay, we cannot do this, then the supplier has to find arguments and causes why it is not possible. So this is not very easy. You have to discuss this with the quality people at the customer company. Okay. So much for today. Next time we will also do the lecture by Zoom at 12:15, beginning again with Q1, and then the second lecture is Q2. So far today, are there any questions from your side? Do you have any questions? Okay, if there are no questions, then I wish you a good time, have a nice week, and until next Wednesday. Bye-bye.
Thanks, bye.